My name is Mikhail Peters, and this is Lab 2, Motion of a Falling Object. The purpose of this lab was to analyze the motion of an object falling somewhat slowly and record its motion over time. This data was then compared to two computational models, one accounting for gravity and the other for both gravity and drag. This lab applied the principles of Newton's second law to attribute the changes in momentum of a system to the application of a net force, which can be seen here in this formula. This can be used to predict changes in velocity, as momentum is equal to velocity times mass. As I preview the results, the observed data fit more closely with the model for both gravity and drag force. Newton's second law states that when a net force is acting on a system, it changes the momentum and therefore velocity over time. This can be seen in the velocity update formula here. If the force is non-zero, we can expect a position over time graph to have a non-linear slope, since the velocity is changing. In this lab, we will examine two forces acting on our paper ball, gravity and drag. Near the surface of the Earth, the force of gravity is given by mass times negative 9.8 meters per second. Drag force, which represents air resistance, is given by the following formula, where B is a proportionality constant unique to each system, and this is given by negative B times the velocity squared times the unit vector of velocity. Here is a procedural overview. I first filmed a video of a paper ball falling to the ground, which I then uploaded to Tracker to record the ball's position at each time interval. I then used GlowScript to create two different computational models to predict the position of the ball over time, one accounting for drag and gravity, and the other for just gravity. I then used Excel to create a plot showing the outcome of both observations and predictions, and then I analyzed the graph to compare the data. Here are the initial conditions for both the code, seen in this screenshot here, and from observations. Our system was the paper ball, the surroundings, the floor, air, earth, and anything else the ball may have come into contact with. The initial velocity was 0 since it was dropped from rest. The initial position was 0.857 meters, and this was calibrated using a sheet of letter paper. The mass was 0.0045 kilograms, or 4.5 grams, and the delta T was 1 over 60, since it was 60 frames per second. And we inputted this here into the code, and what was changed between the two computational models was this B value. I began tracking the motion of the paper ball at rest. I calibrated Tracker with the height of a sheet of paper for reference, recorded the center of the paper ball in each frame, and then graphed the position in Excel using the data given here. And here are the initial conditions as stated on the previous slide. The gravity-only model does not incorporate air resistance, hence the B value is equal to 0. Net force is equal to the ball's mass times acceleration due to gravity near the Earth, which is negative 9.8 meters per second. As time progresses, the gravity-only model and observed data deviate more and more. This suggests that there may be another force acting on the system. The B value for this system was found through trial and error until the endpoint was close to the observed endpoint. In this system, this value was 0.0022. Drag force is equivalent to the negative B times the velocity squared times the unit vector of velocity. Here, the net force is equal to the gravitational force from before plus this drag force. We can see here that this graph aligns much more closely with our observed data. Here we can see that the gravity and drag model, given in green, fits more closely with the observed data given in blue than the gravity-only model given in orange. The curved slope of the position versus time graph shows a changing velocity, and therefore a net force that is non-zero. Therefore, we can conclude that our observed system is likely experiencing both drag force and gravity due to more closely aligning with the gravity and drag force model, and is experiencing a non-zero net force since the velocity is changing. Possible sources of error may include the ball having an initial velocity other than 0, center of mass not being constant in Tracker, and incorrect calibration of Tracker. For the what does it mean question, we are asked in which model terminal velocity is reached. Terminal velocity is reached when gravitational force and drag force are balanced and velocity reaches a constant point. In the gravity-only model, we don't reach a constant velocity as the slope is not flat, but therefore velocity is changing. In the gravity and drag model, the constant slope is reached here, and therefore terminal velocity is reached. This means that the system is experiencing a 0 net force. For the what-if question, we are asked to consider a scenario where the ball is thrown down with initial velocity instead of being dropped from rest, and asked if terminal velocity would change. Based on the graphs, terminal velocity would not change. You would just reach it faster if you already have some initial velocity, as seen here in this graph where it's thrown down at negative 3 meters per second in the y direction. We reach our terminal velocity faster, but our terminal velocity is still negative 4.5 meters per second in both models.